In this part 2 video of photoelectric effect, we're going to talk about how to detect photoelectric effect. So detecting photoelectric effect. If you have a metal and if you are exposing this metal to an electromagnetic radiation, if it has enough energy, it could kick electrons out of this metal. This effect is called photoelectric effect. It doesn't happen all the time. The electromagnetic radiation must have some minimum energy for kicking out the electrons. So how do you know if photoelectric effect has taken place or not? For detecting photoelectric effect, we use such a setup. We call it photocell. So photocell has a vacuum tube, and inside vacuum tube there are two metal electrodes. Anode is connected to the positive terminal of the battery, so anode is positively charged, and cathode is connected to the negative terminal of the battery, so cathode is negatively charged. There is an ammeter connected in the circuit as well. So ammeter measures the current. If there are electrons flowing through the circuit, ammeter shows a deflection. It shows how much current is flowing through the circuit. Now, the cathode is coated with an alkali metal, let's say cesium. Now, if you expose this cesium metal to a UV light source, you can see there's a deflection in the ammeter, a deflection. There are electrons flowing through the circuit. There is current in the circuit. Where are these electrons coming from? So this UV light source, it emits ultraviolet radiation in the form of photons, UV photons. So we have photons. So these photons have enough energy to kick the electrons out of this cesium metal, and these electrons are flowing through the circuit, creating a current in the circuit. In short, photoelectric effect has taken place. The electrons are coming out of the cesium metal, and these electrons are flowing through the circuit, and that is creating a current. So this is how we detect the photoelectric effect. Now let's use the same photocell, except this time we are exposing the metal to a visible light source. So there is cesium metal. When it is exposed to visible light source, there is no current. Ammeter shows 0. There is no current flowing through the circuit. There's no current. What does that mean? There are no electrons flowing through the circuit. Electrons are not coming out of cesium metal. The circuit is broken, right? That's why there is no current in the circuit. So that means there is no photoelectric effect in this case. So we use the same circuit, we use the same metal. The only difference is the electromagnetic source, right? So in this case, we used a UV source, and in this case, we used a visible light source. So what's different between these two? UV has higher frequency compared to the visible. So the frequency of the electromagnetic radiation matters, right? There should be a minimum frequency for the photoelectric effect to happen. Higher frequency means high energy. Lower frequency means low energy. Energy is HF, right? H is a constant, so energy is directly proportional to frequency. Higher frequency means higher energy. Lower frequency means lower energy. If we go back to the energy levels, there are a lot of energy levels. If an electron is here, let's say this is 0 and this is 10, we must use an electromagnetic radiation that emits photons with at least 10 electron volt of energy to take the electron out of this metal to the outermost energy level. So this minimum energy for the photoelectric effect to happen is called the work function of the metal. So work function, it's a minimum energy, in this case 10 electron volt. So it's a minimum energy the electron has to spend to come out of metal, or the minimum energy for photoelectric effect to happen. So I'll write the definition for work function here. The work function is the minimum energy required by the electron to come out of the metal. Work function is the property of a metal. For different metals, work function would be different. So let's say in this case, the work function is 10 electron volt. So how do you write the equation for work function? Work function W or phi we use W or phi to represent work function. So work function is equal to HF0. So this is the minimum energy, right? Minimum energy, and energy is directly related to the frequency. So this must be the minimum frequency. So work function is equal to Planck's constant times the minimum frequency. There is a name for this minimum frequency. It's called threshold frequency. Threshold frequency. So in other words, if a metal has work function 10 electron volts, you must use an electromagnetic radiation that can emit photons with at least 10 electron volt for photoelectric effect to happen. So here we got a table of different metals, that threshold frequencies, threshold wavelengths, and work function. Okay, so cesium has a threshold frequency of 4.7 times 10 to the power of 14 hertz. What does that mean? If you take a cesium metal, you must use an electromagnetic source that could emit photons with a minimum frequency of 4.7 times 10 to the power of 14 hertz to kick the electrons out of cesium metal. So if the photons hitting the cesium metal have frequency of 4.7 times 10 to the power of 14 or higher, photoelectric effect will happen. But if it is less than 4.7 times 10 to the power of 14, there will be no photoelectric effect. So that's the minimum frequency required for photoelectric effect to happen. We call it threshold frequency. So these are the minimum frequency values. Minimum frequency values. Again, for different metals, these numbers are different. For magnesium, the minimum frequency required for photoelectric effect to happen is 8.84 times 10 to the power of 14 hertz. For silver, it is 11.1 times 10 to the power of 14 hertz. For sodium, it is 5.7 times 10 to the power of 14 hertz. So that's threshold frequency. It's a minimum frequency for photoelectric effect to happen. Now, what about threshold wavelength? Okay, so frequency, when you're talking about frequency, there should be a minimum frequency for photoelectric effect to happen. But frequency and wavelength are inversely proportional. F is equal to C over lambda, right? C is a constant, so F is proportional to 1 over lambda. So frequency and wavelength are inversely proportional. If you increase the frequency, wavelength would decrease. If you decrease the frequency, wavelength would increase. Or in other words, minimum frequency means maximum wavelength. So these are maximum wavelength values. Maximum wavelength values. What does that mean? If you take cesium metal and if you're using an electromagnetic radiation with wavelength of 637 or less than 637, photoelectric effect will happen. But if you're using a radiation with wavelength value greater than 637, there will be no photoelectric effect. Same for magnesium. If you're using an electromagnetic radiation with wavelength greater than 339 nanometer, there will be no photoelectric effect. For silver, if you use an electromagnetic radiation greater than 270 nanometer, there will be no photoelectric effect. So these are the maximum wavelength values. Now, how do we convert? We can use the equation F equals C over lambda. We need to find the threshold wavelength, right? So we are talking about minimum frequency and maximum wavelength. So this is the threshold frequency and threshold wavelength. So how do you find the threshold wavelength, the maximum wavelength? C over F0, right? C is 3 times 10 to the power of 8. For cesium, the minimum frequency or threshold frequency is 4.7 times 10 to the power of 14. So if you do that, you will get around 637 nanometer. So that's how you convert. Now, about the work function. Work function is the minimum energy, right? For a cesium metal, you must use an electromagnetic radiation with an energy of at least 1.95 electron volt for photoelectric effect to happen. Okay, so that is the work function, the minimum energy required for photoelectric effect to happen. So anything greater than 1.95, there will be photoelectric effect. So the minimum energy is called work function. So this is again minimum value, minimum energy value. Anything greater than 1.95 electron volt for cesium, there will be photoelectric effect. Anything greater than 3.66 electron volt for magnesium, there will be photoelectric effect.